Okay, welcome back to all of you. This is the second part of the quantum circuit quantization presentation. And as you remember, my name is Kevin Hoven, and today, in the second part, I'm going to talk about, in this case, how to quantize the circuit, but in this case, with a pretty most straightforward way, that is using scQubits. This is a library written in Python in which that can help you in write all of this, analyze the circuit, and it's pretty useful for your research or to teach or to learn all the things that maybe are very you interesting. So before to begin, well, I'm working in Google Colab. Well, the idea is to first of all install scQubits with this pretty easy command pip install scQubits. That's pretty much. I already run the cell, and now the idea is to we import the library scQubits as SCQ. We import NumPy and matplotlib. Okay, so as maybe most of you remember, we was working into the LC oscillator. That was the first circuit that we taken into the account, and we do all the procedure into the quantization. Okay, so but now the idea is not to talk about again into the LC oscillator like manually in the theory. Now the idea is to solve this using SC qubits. So before to that, we need to define our circuit. As you can see here, our circuit is pretty simple, but how I can enter the same architecture into this case, into the library, into the Python, to calculate all this. Okay, so the idea is how to define your circuit. Well, SCQBits have a particular notation in which you need to clarify your device. In this case, your device can be like a capacitor, an oscillator, or also a Josephson junction. Okay, and we have node 1 and node 2. Node 1 and node 2 are referring to the nodes that are connected, the branch. So in this case, just try to assume that we are connecting the capacitor here. So we now have that node 1 will be N0 and node 2 will be N1. And the value is, of course, the value of your capacitor. Okay, great. So okay, now the idea is to try to input this circuit into that test representation. Okay, so the idea is just we call the LC circuit test. This is just a variable. We give it a name like LC circuit and we call branch. And after here, we just try to build our circuit. As I said before, like an example, this is for the C, the capacitance branch, in which we have a capacitor we connected with two nodes, the node 1 and with the node 0 and with a value. A value EC equal to 1. This is just for testing. After that, we have the inductor in which are connected pretty much in the same way in parallel with our capacitor with a value equal to EL equal to 1. After that, we just need to write our circuit. Now this is our circuit representation in which we call the library dot circuit and we path the LC circuit test. This is not from a file and the external basis is harmonic because we are building an LC oscillator. This is okay, but before to all of that, this is our Lagrangian as we calculate the same in the previous video. And now we are trying to build the same Lagrangian using SCQ circuit. Okay, so we just call the dot system Lagrangian or symbolic Lagrangian actually, and we have the same representation as before. As you can see, we call C1 equal to C1, or in this case, not equal to 1 because EC is equal to 1, but C could be different. Instead, actually, to be honest, is different. Okay, as you can see, this is pretty simple, and now we are trying to calculate the same thing using the Hamiltonian. The Hamiltonian that we calculate before in the video is something like this, and if we try to calculate that is using SQ circuits, we can do something pretty simple like symbolic Hamiltonian. Calculating this, we have the same equation as before. Pretty simple. As you can see, we are doing all the calculation related with with the previous video just in a couple of lines. And you can do all of this using scQubits. Okay, now let's try to plot the potential energy. And why? Because we need to calculate how all of this, the energy difference between one level and another level. So if we just do these three lines of code that are pretty simple, we will come out with something like this. So let's try to calculate the eigenvalues of our circuit. These are the eigenvalues, and after that we just try to calculate the difference between one level and another level. So here are the difference level into the one excited state and the ground state, which is 2.82. And the second excited state minus the first excited state is equal to 2.82. They are similar, are the same. We don't need this into quantum computing because we need to have pretty well defined and differentiate between the ground state and the excited state. No more. We need a two-level system. So, in order to solve that, we are using the Josephson junction. Okay, now with the Josephson junction, now this will be pretty simple to calculate. We just call the circuit test representation as before with the LC oscillator. We just call the circuit text, we define given a name, calculate the branches or define the branches, and we just call the JJ, which is the Josephson junction. We call the two nodes that are the 1 and 0 nodes, we give two values that are the Josephson energy and the capacitance of the Josephson energy, or the Josephson capacitance energy. And with that, we need to define the capacitor, which is pretty similar as before. After that, as you maybe remember from the previous video, this is our Lagrangian, and here we just call Lagrangian. We define our circuit and call the Lagrangian into a symbolic way. That is this one, that is pretty similar, or I could say the same as we calculate before. We do the same procedure calculating the Hamiltonian, that is this one, and we just calculate the Hamiltonian given this symbolic Hamiltonian. Now maybe this is a little bit different as we calculate before, but just taking into account that scQubits taking into account or takes into account the ng1, which is correspond to an offset charge, that is this ng1. If we do this like value equal to 0, we will have the same Hamiltonian as before. This is a better way to calculate all of this, and is pretty well generalized instead of our way. If maybe you are wondering why is ET before, in this case, you can do all the calculation given ET, given the case that we have just the value from EC and EG instead of just C and L or CG and C, and you will come out with something like that. Okay, so before to end all of this, let's try to calculate the potential from our circuit as before. So as before, we just calculate the potential, plot the potential, and let's try again to calculate the difference between the energy levels. So as you can see here, the difference between the ground state and the first side state is equal to 2186, and the difference between the second side state and the first side state is equal to 2.27, which is that are different. So that's why we need a Josephson junction to do all these things related to calculate or to do quantum computation, because we have now two levels to do computation. Okay, yeah, as I said, we need this for quantum computation. Okay, great. Here we just try to compare the potential, and you can see one of these are pretty like x squared, and the other one are like a sinusoidal sine, as you can see. That is why it's a non-linear way to calculate all of this, and we have all the difference. Okay, so thank you so much. Thanks to all of you. If you have any questions, you can comment on the video, put into the comments, and also please take a look into the scQubits. That this is a pretty good library to work with and also to do research. Thank you so much and see you soon.